Hello, in this video I'm going to talk about defects in crystalline solid. So then what are crystalline solids? They have a regular pattern of arrangement of particles. They have a definite geometrical shape and a sharp melting point. It has cleavage property. Now what does that mean? It means if you cut a crystalline solid, the two newly formed surface will be smooth. Another very important property is that crystalline solids are anisotropic. To explain this, check the diagram. The two arrows come across different arrangement of atoms in different directions. So the property is different in different direction. Remember, crystalline solids are formed by cooling the melt very slowly. If the rate of cooling is fast or at moderate rate, then defects are formed. The first type of defect is line defect. This is irregularities in the arrangement of atoms in an entire row of lattice. The second type is point defect. This is irregularities around the particle or atom. Now this defect is more important. There are three types of point defects. The first type, stoichiometric defect. This does not disturb the stoichiometry. That is, ratio of the cations and anions are same. That means the stoichiometry is maintained. This defect is due to the arrangement of atoms or ions in a crystal, and so it is called as intrinsic defect. In non-ionic solids, there are two types of stoichiometric defect. The first, vacancy defect. Some of the lattice sites are vacant. That is why it is called vacancy defect. Now this happens when the crystals are heated. Now due to the loss of atoms, the density decreases. The second type of stoichiometric defect found in non-ionic solid is interstitial defect. In this, atoms occupy interstitial sites, so density increases. Now, if you check the diagrams, it explains both of the defects. In ionic solids, there are two important stoichiometric defects. First, Frenkel defect. In crystals where the cation is small, the small cation moves to the interstitial site from the lattice site. So, the lattice site is empty. This is a combination of vacancy and interstitial defect. Remember, density will not change. Examples of solids exhibiting Frenkel defect are silver halides and zinc sulfide. Now remember, alkali metal halides have a large cation and it cannot exhibit Frenkel defect. The second important defect in ionic solid is Schottky defect. Now this is a vacancy defect where equal number of cations and anions are missing. It's found in crystals where size of both the cation and anions are almost of equal size. There will be a decrease in density. Alkali metal halides exhibit Schottky defect. Remember, a solid which shows both Frenkel and Schottky defect is AgBr. Now, due to these defects, a crystalline solid will conduct electricity to a very small extent. Remember, a perfect crystalline solid would not have conducted electricity. Now, due to holes, the stability of the solid will decrease. Now, in Frenkel defect, similar charges come close by, and as a result, the dielectric constant will also increase. The second type of point defect is non-stoichiometric defect. In this, the number of cations and anions are different. That is, stoichiometry is not maintained. But remember, electrical neutrality is maintained. The first type of non-stoichiometric defect is metal excess defect. Under this, the first type is due to anion vacancy. To understand this, let us take an example. If a crystal of sodium chloride is heated in sodium vapor, the sodium atom settles on the surface of the solid NaCl. Cl- from the crystal moves to the surface. Sodium atom loses an electron and becomes Na+. The electron moves to the anionic vacancy left behind by Cl-. This site, which is now occupied by an electron, is called F-center. Let us check the consequence of F-center. An unpaired electron can be responsible for color as well as conduction of electricity. Thus, presence of F-center makes sodium chloride yellow, potassium chloride violet, and lithium chloride pink. Another metal excess defect is due to extra cation in interstitial site. Let's take zinc oxide as the example. It is found that ZnO is yellow when hot and white when cold. This happens because when ZnO is heated, it loses oxygen as shown in the equation. The electrons and Zn2+ occupy interstitial site. These electrons are responsible for the yellow color. The number of Zn2+ is more than O2- ions. On cooling, the oxygen becomes oxide ion and returns to the lattice site. So, ZnO is white on cooling. Another non-stoichiometric defect is the metal deficiency defect. Compounds having metals with variable valency show this defect. Example, in ferrous oxide, some Fe2+ is oxidized to Fe3+ ions. In order to maintain electrical neutrality, some Fe2+ are missing. Thus, ferrous oxide can have different amounts of Fe2+ ions. Now, let us solve a problem based on metal deficiency defect. Analysis shows that nickel oxide has formula Ni.9801. What is the percentage of Ni2+ and Ni3+ ions? Now, to solve this, let Ni2+ be X. Then Ni3+ will be 0.98 minus X. To solve for X, let us form an equation with charges. Now, Ni2+ has a charge +2, so it will be +2x, while Ni3+ will be +3, so +3 into 0.98 minus x. Now, -2 is the charge of an oxide ion. On solving, x is equal to 0.94, so the percentage of Ni2+ will be 96%, and that of Ni3+ will be 4%. The third defect found in crystals is impurity defect. This defect is formed by adding an ion of different valency. Let us take an example. If molten NaCl is crystallized with strontium chloride, then some of the sites are occupied by Sr2+ instead of Na+. In order to maintain electrical neutrality, one Na+ is lost, creating a vacancy, and one Na+ is replaced by Sr2+. Thus, the number of cationic vacancy is equal to the number of Sr2+ ions. Let us pass on to a problem based on impurity defect. If NaCl is doped to 10⁻³ mole% of SrCl2, what is the concentration of cation vacancy? Since it is mole%, 100 moles will contain 10⁻³ moles of Sr2+. So in 1 mole there will be 10⁻⁵ moles of Sr2+. Since question is concentration, we will multiply moles with Avogadro number. Remember, the number of Sr2+ is equal to the number of cation vacancy. So, the number of cation vacancy is 6.02 into 10⁻18. Hope you have understood the defects in crystalline solids. Thank you.